In this video, we're going to be doing 3 Unit 7 oscillations and springs, FRQs, for AP Physics 1. Before we start, you can go into the description and download the PDF that contains these 3 FRQs and practice along, or try to solve them yourself. So we have, firstly, a block of mass m attached to a light vertical spring of spring constant k hanging from a rigid ceiling. The spring stretches a distance xe from its unstretched length, aka equilibrium, when the block hangs at rest. The block is then pulled down an additional distance, a amplitude, below the equilibrium position, and released from rest at time t is equal to 0. Let downward be the positive direction, and air resistance is negligible. On the diagram above, draw and label all the forces acting on the block immediately after it is released. So we have on the center of the mass the force of gravity, and we also are going to have the force of the spring that is acting upward since we are displaced from equilibrium. And it's going to equal to our k times our xe plus a. Because the block is below equilibrium, the spring is more stretched than usual. So that's why our spring is going to pull upward harder than at the equilibrium. So because our downward direction is going to be our positive direction, we are going to have that Fg is equal to mg is going to be positive, and we're going to have Fs is equal to negative k. Here, this is going to be negative. So if we take this net forces for this situation, we have F is equal to mg minus k xe plus a. So our block is below equilibrium, which is why our spring force is larger than the gravity, and it's pointing back towards the equilibrium. So it's actually going to bring us back up. Now, for part B, we're asked, using Newton's second law, derive an expression for the equilibrium stretch xe in terms of mg and k. So if you are at equilibrium, that means that you currently have 0 acceleration, because acceleration, it always points back towards the equilibrium. However, if you're already at your equilibrium, then your acceleration doesn't have to point back towards equilibrium. So we can use Newton's second law, F is equal to ma, and our downward direction was positive, so we have a positive mg, and we have a negative k xe. So mg is equal to kxe. Now we know that we can solve for xe, so we get this expression here. So when we're at equilibrium, our upward spring force is going to balance the downward weight perfectly. Now for part C, we were asked to let y represent the displacement of the block from equilibrium, with downward is positive. Starting with Newton's second law, derive the equation relating acceleration and displacement y. So you have that the total is this. Fg is mg, spring force is negative k. That's equal to ma. So from part B, we have this expression, that relationship, so we can substitute that here. Instead, we can write a kxe here if we distributed that. So then you can write mg minus ky is equal to ma. So a is equal to negative k over m times y. So our acceleration is now for the energy bar chart, we have the system of these 3. So EQM, UG0, displacement y is from the equilibrium. So when we are already stretched, we already stretched XE from EQM already. So you also already have gravitational potential energy. Downward again is positive, and EQM is 0, so UG is equal to negative my, because moving downward is going to lower your gravitational potential energy. So at release, you have and you also have so you have kinetic energy of 0, US of that, and negative MGA. Now when you're at equilibrium, you have Y is equal to 0, US is equal to 1/2 KXE squared, UG is equal to 0, K is max, which is 1/2 KA squared. So for highest position, we have Y is equal to negative amplitude. We have the block is momentarily at rest. We have US is equal to 1/2 K XE minus A squared, and UG is equal to positive MG times A. So at each of the turning points, your speed is 0. At equilibrium, you have the max speed. Derive an expression for the maximum speed and the period of oscillation. We already know that A is negative K over M. We have A is equal to negative omega squared times Y. Also, we have this relationship. So omega is the root of this. We have Vmax is equal to amplitude omega. So you can just substitute in omega right there. You get your answer for Vmax. Period, though, is 2 pi over omega. So you have 2 pi over root of K over M. 2 pi is the root of M over K. So all we have is that the force of gravity shifts our EQM position. It doesn't change the oscillation frequency about EQM. Now, for part F, we're asked if what's going to happen if we use the same spring, but with 4M, and the block is released again from the same amplitude. A, about its new equilibrium position, we want to find how Vmax and period change. Originally, we had Vmax is this. Now we have 4 times our M. So the ratio is 1/2 of Vmax for V new. For period, we have this. Now we have T prime. So you can take that 4 out. And we can see T prime is just twice that of T. So logic is that increasing mass will make your oscillator harder to accelerate. So Vmax decreases, and the time for one full oscillation period is increasing. Let's say for our second FRQ, a block of mass m is released from rest at a height h above the top of an uncompressed vertical spring of spring constant k. The spring is fixed to the floor. The block rests vertically and makes contact with the spring and compresses the spring a maximum distance x max. Assume the block remains in contact with the spring after first touching it and that air resistance is negligible. So on the diagram, we want to label the forces acting on the block while the spring is partially compressed and the block is still downward moving. So when we're moving downward, we still have Fg. Spring force is Kx upward once it reaches down. So that means we're actually here. Because we want to go back up. Let's make downward our positive direction. So then we can say so gravity pulls the block down and the compressed spring pushes up. Complete the energy bar chart for the system before contact with the spring at max compression and just before contact, and also release. Okay. So when you're at release, you are at h above the spring. So K is 0, US is 0, and UG is MGH. Now for the next scenario, before contact, we fell down H. UG is 0, US is 0, and K is MGH, equal to what MGH was, but you know the formula for that is still 1/2 mv squared. So all your energy is kinetic. Now, when you are at max compression, K is 0, because you have 0 velocity, because you're momentarily at rest. Your spring compression is X max, making US equal to 1/2 KX max squared, aka it's max. UG is equal to 0, because Y is equal to 0 at this point. So, also here, you're just at the top of the spring, by the way. So Y is equal to 0 here, though. So UG is equal to negative MGX max. And technically, we can't graph that negative MGX max, but we're going to say that all of our energy is spring here, because it's just spring. Now, we're asked to derive an expression that can solve for X max in terms of MGH and K. Let's have our conservation of energy. Initially, 0. We have MGH, and we have 0 here. Then we have 0. So this side is the initial release, by the way. This is the final compression. We have negative mgx max, and we have 1/2 k x max squared. mgh is equal to this. We can just move that to the other side, actually. So we have 0. And you could also factor this when it was like this, and also move that 1/2 kx max to one side. So for part D, we're asked to determine the magnitude of the spring force on the block with the maximum compression terms of K and X max. Then compare this force with mg and explain why the block is instantaneously at rest, but not in equilibrium at max compression. So for part D, when we have max compression, Fx is equal to K times X max. So if we compare this with mg, we have Newton's second law at this point. So let's say it's at equilibrium. And for the block to be in equilibrium, this is our requirement. That would require mg minus k max, x max to equal to 0, and kx max to equal to mg. However, at max compression, after being dropped, the block is at a turning point, not equilibrium as we know. And again, when we are at max compression, the Fs has to be greater than the weight so that our acceleration can point up and the block can reverse direction. Therefore, that's how we know Kx max is greater than mg, even though that v is equal to 0, the acceleration is not 0. So if we go back to Newton's second law, we know that we have mg minus kx max is equal to max times acceleration. So then we know that kx max is greater than mg. So a is less than 0. So a is not equal to 0. It still can be negative or it can be positive. But if it is negative acceleration, we have actually that meaning upward acceleration because downward is positive here. As in its upward acceleration. So momentarily at rest does not mean equilibrium because equilibrium requires 0 net force. So for part E, we are asked, does this period of the resulting vertical oscillation depend on the drop height of h? Explain your answer. So at E, your EQM compression after oscillation begins. And when we have Newton's second law at EQM, forces are 0. Downward is positive. This is equal to 0, so mg is equal to kxe, and we have mg over k. So at EQM compression, we have that upward spring force balances weight. We're asked, does the period of the resulting vertical oscillation depend on the drop height h? No, it doesn't, because we have 2 pi is equal to the root of m over k still for a vertical mass spring in simple harmonic motion. So there is no h, because a vertical height drop changes the amplitude. And we have that acceleration is equal to negative k over m times y, which y is our displacement from EQM. So what that means is that if you have a block and you just drop it from a higher height, that means that it's just going to go down more, and then it's also going to go up more because you gave it a larger UG, you gave it a larger initial gravitational potential energy. So because it conserves that gravitational potential energy, it's just going to give you more energy to keep going back and up and down. So again, when you think of a sinusoidal wave like this, if you have this as like your period and this another 2 times your period, and you have like a curve that's like this, so you have something that's like this and then like this, if you increase your drop height, what's actually going to happen is not going to be faster. It's just going to increase your amplitude. So it's just going to be like this. Now for our next question, we have a block of mass m rests on a frictionless horizontal track and is attached between 2 identical springs, each with a spring constant k. The left block is attached to a fixed wall on the left, and the right spring is attached to a fixed wall on the right. When the block is at x is equal to 0, the springs are both at their natural lengths. The block is displaced a distance a to the right and released from rest. On the diagram, draw and label the forces exerted by the 2 springs on the block when the block is displaced to the right by a distance x. So, we go to the right. We have that the force to the left is equal to kx. That's for the left spring, because our left spring is going to be stretched by x. Now, what about the right spring? We have kx to the left. It's pushing or we have that the right spring is compressed by X. So we have that it pushes block to the left. They both push the block to the left. So if we make our right direction positive, because that's where we're moving, we'll have that FL is going to be negative KX, FR is negative KX, because they have to be negative, because they try to restore the block back to X is equal to 0 EQM. Now, starting with Newton's second law, derive the net force on the block as a function of displacement, X. We have a summation of our forces in the X direction. So that's our net force. For part C, we want to complete the energy bar chart for the spring we want to determine the spring constant K effective for this system. So for a single effective spring, we already know that F net is equal to negative 2kx. So we get this. Part D, we're asked to derive an expression for the period of oscillation. Any mass spring oscillator is 2 pi the root of m over k effective. K effective is 2k. Period is 2 pi the root of m over 2k. So Newton's second law, we get this. So we also have our simple harmonic form. So this means that omega is equal to the root of 2k over m. We also know period is 2 pi over omega. So then period, substituting that in, we get 2 pi over 2k over m. And then we're going to flip this and then put this up here. So we have 2 pi times root of m over 2k, flipping the inside of the contents. So because the two springs, they increase the restoring force, you can write this. period decreases. For the energy bar chart, we have the sum of the spring energies. So the spring changes by a length of x displacement. So each spring stores which is just us knowing those formulas we have. So we get a total of just kx squared, because 1/2 and 1/2. What about x is equal to a? So k is 0. Now what about the left spring? We have the right spring. So we have these both. So here, if we have x is equal to 0, we have they're both at natural. So k max is going to be everything. At negative a, you have k is 0 again. And we have that they're both equal to 1/2 again. So our energy is just alternating between kinetic at equilibrium and spring potential when you're at the turning points. Derive an expression for the max speed of the block. So we have energy conservation, no friction. So this is going to be x equals to a, and this is x is equal to 0. Kinetic energy. So here we have all of this US. This is equal to 0. One half mv squared max. So our block is fastest at EQM. So all that, if they have both potential spring energy equals to 0 there, that means that all the energy has to be kinetic. So the student claims that there are 2 springs. That means that the period must be twice the period of a single spring oscillator with a same mass and spring constant k. Is the student's claim right? So the claim was this is wrong. Because for one spring, for 2 pi over the root of m over k. Now 2 identical springs. Now if we compare, the only difference is 1 over the root of square root of 2 pi root of m over k. So if you have 2 springs, that creates a larger restoring force, so the block accelerates back towards equilibrium more strongly and oscillates faster. That makes sense because if you have those 2 springs, it makes sense that there would be a spring force on either side, and they'd both be encouraging it to stay at that position more than if you just had an unbalanced one spring on one side. So that makes sense, like if you think about it physically too.